Good morning to one and all over here. Uh, it's my privilege to introduce today's guest, Dr. Chandramouli S V, sir. And sir has a 20 years, 6 month professional experience in academics and industrial practice. He involved in national and international projects. And sir honored as a best professor in civil engineering studies at the 17th Devang Mehta Business School Award 2019. And previously, sir worked as a professor in the Department of Civil Engineering, PS University, and SHM consultant, SCMCS, manager, SHM, and manager at Sevcor India, technical manager, structural engineer in SECON, and authored more than 20 plus papers in reputed journals with international and national conferences also. Okay, trained 50 plus interns and guided more than 30 plus ME MTech students for their final graduation, that is ME MTech thesis. An active member of ASCCE, IABSE, ISHM, IISSS, and so on. And presently, the sir is working as a structural art and SMH consultant at SCMCS Bangalore. Sir, it's a privilege to have a guest today, and over to you, sir.
Thank you, Professor Mantesh Koti, for the kind words and introducing me. I hope we are in the classroom and filled with students, and I think they have their test as told by you at 12. I'll try to keep my presentation as short as possible and as interesting as possible, and I've not included any of the derivations or equations since we are not next to the board, and since it's an online, I prefer it to be of more in high catchy. So therefore, the students get interested in the subject, and there are eminent professors at PS University where I was previously working who will be enlightening you on the subject in the later days. Before I start my presentation, I would always acknowledge all the teachers for their contributions for what I'm at today, and I believe in the principles which my gurus had taught me. So I always believe in one of the great statement: when the student is ready, the guru will appear. So and as well, you should if you look into the great Adi Shankaracharya's Guru Ashtakam, it gives you the more it tries to enlighten you on the importance of guru. So I would like to revert to all the gurus. I've been joined with a few of my colleagues, earlier colleagues, as well as my students who were of my with when I was teaching there at PES. So I thank them all, and I thank them for appreciating me. Now, I believe that before I start my presentation, I would like to introduce to one few of my experiences, earlier experiences, and the participants or the students who are listening in the later days. If in case they have some queries, they can always reach and reach and get some clarification on the subjects which I'm involved in. So the only source of knowledge is experience. As a student, I think you are gaining knowledge at the department, and you have labs and you have various other activities which enriches you, and which also gives you the skill set. So definitely those experiences are prime important. Now, as I said, I was at the PS University at the Department of Civil Engineering as a professor, and the picture which I placed there is of the last day where I was working at that department. Previous to that, I was into the structural health monitoring and as well as business at various organizations, and a few of my projects are shown here. These are very relevant for mechanical engineers because the vibration aspects, which you call it as vibration analysis and vibration diagnostics, condition monitoring, prognosis, these are the things that you would be these are the words that are associated with structural health monitoring, and these are few of the projects which I was involved in during the construction stage as well as during the various other stages of civil infrastructure. And most of the projects were in abroad, since these were the large tall structures which requires vibration monitoring. And Post that, before that, I had also worked in companies which was involved in repair and rehab. So today's the topic is related to the columns. Now, in one of the companies previously where I was working, this was an issue, and I would show you some of the pictures. You can see here, this is one of the largest industries in the world. It's renowned the third largest in the world. And if you can see here, you can see that there is a column that is buckled. So I was one of the technical expert to retrofit this particular structure, and you can see that the why the subject is being given to me today by Mantesh Koti to present to you all and give you the relevance of this and knowing what is the importance of it and what is it, I mean, how these basics are very important when you're solving such practical issues on site. And to your surprise, this is not a small building, it is quite large building. And you can see, I will show you the scale of this building. You can see this man here who's standing, and you can easily locate, you can see that the building is raised almost by 1 meter. Okay, that's the lift there is going to be, and because of that the column had buckled. So you can see this is the status of the building. Okay, and you can see this is the column, and if you want to relate the size, you can see here. Okay, you can relate the size of the column. It's almost as wide as your shoulders. That is almost about 2 feet. So that's a quite huge column, but as I said, it's almost buckled about 1 meter. You can see here the buckling that took place. Okay, so this is quite relevant and it's quite practical, as well as if you know something about buckling that happens locally also. You can see at the same site you had a lot of local buckling, for which knowing these basic concept of column buckling, we have provided some of the retrofitting schemes for the whole entire building or the structure. Now you can see these are the retrofitted structure which we are provided with a these are called bracings, and we are provided with cross bracings. Okay, so this was done, and we have also given, since this is related to stability issue, we have tried to counteract the stability, and we have provided some inclined columns, and this is still the ongoing project that is being retrofitted since long back. So therefore I greet one and all for this day, for being this day, and I thank Professor Mantesh Koti of the Mechanical Department, PS University, for inviting me for as a guest speaker for the subject on mechanics of solid, in particularly the topic on columns. Now I've titled my presentation as Euler's column buckling load, introduction and concept. Before we continue, can I get a confirmation? Am I audible to all?
Yes, sir. Yes, sir.
Yeah, thank you. So, as I said, the topic of today's lecture is focused on columns, stability, Euler's formula, and so the lectures will be more concentrating on the column buckling. And let me tell you that this particular lecture is going to be as simple as possible, so that the student get interested in the subject and start learning on the subject further. Now, the outline of my presentation are the basic terminologies of any engineering design. We'll look into some of the 2D linear members. Although we will be concentrating on columns, you should also know where these buckling can occur. The compression member, and we'll also look into the various type of failures. Then we have the Euler critical buckling, the end conditions and the buckling load, buckling stresses, effective length coefficients, limitations of the Euler's theory, and the examples of column failures in civil engineering, because I'm a structural engineer, so I would be showing some of the civil engineering failures. Okay, so let's start with the basic terminologies of engineering design. I believe that any student who would like to get into some subjects should always have some of the prerequisites, like knowing the terminologies or basic equations and basic definitions. Now, the task of any safe design, what we call in engineering, any safe design, we say any design is safe if it satisfies these three conditions, that is strength, the rigidity, which is also known as the stiffness, and the stability. The economy, efficiency, these are the terms that should be always by default in any engineering design. So that also takes an emphasis in the later days when you're talking about the economics. So therefore, for any safe design of engineering, the three components are strength, stiffness, and stability. Now, before we continue, so you should understand the definitions of these. The strength of the structure is its ability to support the required load without experiencing excessive stress. This is what you've been learning, and for this, again, you should know the definition of a force and a load and the stress. Now we are talking about the strength. Therefore, we are talking about the forces that are induced or interacting with the structure. Therefore, it is the load, and the stresses are nothing but the internal forces, the internal resisting forces. So the strength of the structure is the ability to support the required load without experiencing excessive stresses. Now there are various definitions in the various books, and I think I've just read only the simple one. Now you can, if you go through the books, but if you have not gone through the basics, then there could be a lot of confusions related to this. So let me read one of the definitions which I've taken it from a standard textbook. The ability of a component or the part to resist damage, within bracket fracture, or significant deformation under the influence of an external force. Now here the damage is a definition that is defined by various people in various ways. So a crack is a damage, critical damage, you have simple damage to most complex damage. But in engineering, if it is not optimally functioning, if any structure or any engineering component is not efficient, or if it is not functioning rightly, then we call it as damage. Therefore, understanding any terminologies or understanding any definitions, they requires the complete detailed understanding of those terminologies. So there's few more definitions. Strength is a parameter that reflects the failure of a material such as fracture. Now, generally, when you are speaking about strength, we are more interested about the tensile strength and the compression strength. Now, you know the units of strength is given in MPa, it's megapascals. And it is also equivalent to newtons per millimeter square. Now we are dealing with all SI units, therefore I have tried to show you that. So we have understood the definition of strength. Now let's look into the stiffness. And again, as I said, these are the major three components for the safe engineering design. The stiffness is also one of the criteria. So the stiffness of the structure is the ability to support the required load without undergoing excessive deformations. Now as you can see here, we have again the load, and the next word is the deformation. So I hope you know what is the definition of deformation. Now, in a simple terms, most of the time, if you are into college books, and most of the time students are more into the subject called computer structural mechanics or matrix method, or finite element method, they also sometimes tend to define this stiffness in terms of the spring. Simply for the spring, the tension divided by the elongation is called stiffness. So here you see the tension is nothing but the force, and the elongation is nothing but the deformation, and this is defined as stiffness. The unit of stiffness is Newton per meter. Now you can see here the member, the component, that is a spring which has got the length L, is deformed at delta. It deforms by delta when it is subjected to P. Now, by definition, if you can see here, P is equal to K delta. Or if I want to know the stiffness of the spring, all that I have to do is the K is nothing but the stiffness of the spring. So I get P by delta is equal to K. Simple. Now there are various definitions again in various textbooks. You can look into that. This stiffness is the ability of the component or the part to resist elastic deformation. So we are talking everything within elastic limit and the first order theory. So the elastic deformation or displacement, although these two different words are different, in this context it means the same, but although they are quite different, you have to look into the books for understanding what is the deformation and the displacement. So again, here the stiffness is a parameter reflecting the relationship between the deformation of the structure and the magnitude of force. Now the amount of deformation produced by how much force the structure is subjected to is defined as stiffness. So, in simple words, this is a better one. The tension divided by elongation is the stiffness. The most simplified one is the stiffness of the structure is the ability to support the required load without undergoing excessive deformation. So, we have understood the two definitions. Now, let's look into various types of stiffness. We have static stiffness and dynamic stiffness. Now here the load which is gradually applied, which does not induce any initial force, and there is if it is a constant load, then it is called as a static stiffness. Whereas if it is alternating and induces the inertial effects into a system, then we will be looking into the dynamic stiffness. Again, the static stiffness can be further classified as structural stiffness, and there are contact stiffness, which more of mechanical guys will be definitely looking into in the later days when you're dealing with structures or components. Now, again, in the types of stiffness, we have various types of stiffness depending on the force it is being subjected to. Any component has a stiffness, and this stiffness can be defined with respect to the forces it is being applied to. So we have the axial stiffness, shear stiffness, bending stiffness, and torsional stiffness. Now, as we saw that the theoretical understanding of strength and stiffness is understood, the definition of strength as opposed to stiffness, that is, I'm talking about the strength, addresses the destruction by external force. Now, you know that when there is a strength applied onto some system, now you can easily see some type of adverse effect onto the system because of the external force. Now, because of these, the destructions can be, or the adverse effect that is caused by because of the strength that is applied or the stresses that is applied, you see some type of yielding that takes place. These yieldings can be classified again. You have the plastic yielding, and you have the yielding can be elastic, plastic, and sometimes you have the brittle failure. So in order to understand this, we always look into the stress strain curve. So I think you have your labs, and in your labs you've done this tensile test on the steel, and you also looked into the stress strain diagram, which is very important, which is very fundamental for understanding the strength of materials. So presuming that you know all the definitions that is underlaid in the stress strain diagram, I would be continuing further. So some of the important properties for the design when we talk about strength and stiffness, and is also that we need to know something about the stress strain curve. And in the stress strain curve, we need to know the definition of each of these terminologies that is there in the stress strain curve. So I will just try to skip these because of time, and you have to know that a few of the terms to read out are stress strain, the elastic behavior, the plastic behavior, resilience, toughness, and ductility. Now, whenever you subject any system or subject to tension forces, it deforms. Now you have a stress strain curve, and because of the strength that is being applied onto the structure, it would damage, or it would alter, or it would have an adverse effect. Now, as you can see, it would have the two type of failure, that is a brittle failure in case of a brittle material, and it will have a plastic yield in case of an elastic or a plastic material. Now you can see that the specimens that is used in the tensile test, you have the ductile failure and you have the brittle failure. Now, if you look into the microscopic, level, now when you're subjecting any system to the tensile forces, that is, we are talking about the stress strain curve, and now for the tensile element, let's take one of the elements here, and I'm taking a very small unit area. That is a small area, microscopic area, and you see the initial conditions how it's been, the what you have the molecules, or you can call it as the smallest individual component of a system or a material. If you see the initial condition, it is intact. But when there is a small load, you can see there is a stretch. Now the stretch is going to be within the elastic limit. So because of the force that is applied, there's going to be a deformation, and that deformation in the microscopic level you can see as a stretch. And upon unloading this, it gets back to its normal initial condition. But these four can be, the elasticity can be linear or non-linear. When it takes a linear path, when it comes back, it returns in a linear curve. then it is called a linear elastic. If it is doesn't, if does it doesn't, then it undergoes non-linear. It is called as non-linear elastic. So these elastic means it is reversible. So although the deformations are there, these are elastic deformation and the elastics are reversible. Now we have plastic deformations. So these plastic deformations are that when you apply a force and you cross a limit, and you have the elastic deformations and as well as plastic, and you can see that the microscopic components are being affected, and thereby it doesn't return to its original position as in the earlier stage. So therefore there is a deformation here. So that means there's some permanent changes that is going to take place, and you can see from the stress strain curve. So the stress strain curve plays an important role. As you know, the slope of this line in the elastic limit gives you the stiffness, the elastic stiffness. Okay, the energy between this, so it gives you how much of energy is stored within the body. So very important is the stress strain curve. Now if you look at the microscopic level, as you further develop in the later days when you're doing your post graduation and you're doing your doctoral studies, the microscopic behavior of any system is very, very important. As you can see, the fracture surface for the brittle, ductile, and as well as the those elements that are between both, which shows the characteristics of brittle and ductile, are shown in this particular picture slide. So you can easily see, how the ductile element would look in the microscope, and as well as the ductile and the between the materials that is between ductile, brittle, and ductile. Now, when you have a stress strain curve, you can define the whole system. You can give various definitions for the system. You can call the system as high strength. You can call that system to be more ductile, or you can call the system to having the higher stiffness or highly energy absorbent. Now you can see the carbon content, which is a main component when it comes to steel. It defines the strength of the steel. Now, high the carbon content, it becomes stronger, and you can see the medium and the most ductile, so lower carbon content. Now, when I take this curve, you can say which of this is the toughest, which of this is most ductile, and which of this is most strongest. So you can see here the strongest means the strength is high, whereas you can see the stiffness is very, very high. Now the steel, the medium carbon steel, the toughness, you can see the toughness is very high because you take out the energy absorption. Now when it comes to ductility, you have the both energy absorption as well as the straining ability, so you have called that as most ductile. But if you look at this steel, the steel itself, all these which are, whether it is high, medium, or low carbon, all are having the stiffness. So stiffness also can be defined. So knowing the stress strain curve, we can define the various parameters that are involved in your engineering design. So now the last practical thing that needs to be done in practice, apart from the strength and as well as the stiffness, we have the third concern with most of the structure, that is the stability of the structure. The stability of the structure is the ability of structures to support the required load without experiencing a sudden change in the configuration. Now we are talking about the configuration. This configuration change can really impact the whole structure. Now, stability is, it's a very common thing. When you're making a discussion with your friends, you say somebody is unstable. You know what you're trying to tell. So the stability, it's not necessary to be you not understand stability. It's not necessary for you to be some type of a structural engineer to have a sense of what it means for a structure to be stable. Okay, so it's a more of a common word. Most of us have an inherent understanding of the definition of instability. You can say a person is unstable, that a small change in the load will cause a large change in the displacement. So this we have seen in most of the things. So if the changes in the displacement is large enough or is in the critical member of the structure, a local or the member instability may cause collapse of the entire structure. So you can see some of the you can say that, although this person is on the wheelchair, you can still say that he's stable. Now you have the rocking chair here. Okay, you have the rocking chair, and you can say it could be a neutral stability, or you have the condition here. There could be a loss of stability sometimes, so it could be unstable. Now, stability of equilibrium can be of three categories, that is stable equilibrium, unstable equilibrium, and neutral equilibrium. The classification of stability. Now, if you look at this example here, the stability of equilibrium, you have the pin joint here, and you can see here there is a post that is suspended, or that is being pinned to this particular, hinged to this particular point. Now if I make a smallest change in this configuration, this would fall, and therefore it becomes unstable. Whereas this is like a pendulum type, and I just try to move away from this initial position or the equilibrium position, it will try to swing to and fro. Now here you have a different condition wherein it is quite balanced. So this is called the neutral equilibrium condition. So you can see the differential, you can see the analogy of this. If the ball is on this particular convex, so therefore if you just move it up, if you just disturb it, it will fall and it will never return back to initial condition. Whereas you have the concave here, and if I move the ball to this limit and leave it up, and it will try to swing to and fro, therefore it is in the stable equilibrium condition. Now you have the nuclear equilibrium condition when the ball is resting on the flat surface. Now, the factors for stability, and whenever you think of a stability, are nothing but the mass of the object, the location of center of gravity, and the area of the base of the support. If you look at these three diagrams, you have a triangle, you have the pyramids, which are the quite large. We see whenever I conduct classes for architects, I've been asking them what is the difference between the pyramid and as well as a bowl. The globe, it looks quite unstable, whereas this pyramid is quite stable. This is the reason is because of the area of the base. Although the globe has the center of mass at the center, but this pyramid, the center of gravity or the center of mass is quite low. So when you're designing as a mechanical engineer any vehicles, the F1 vehicles or the vehicles, the supersonic speed vehicles, you try to bring the CG as low as possible. Now if you look at this condition, it's the CG is above, the mass is also being concentrated above, so therefore there's going to be, the base is quite low, therefore there's going to be instability. So this is stable, unstable, and this is neutral. So you have these conditions. Therefore the factors for stability are the masses, the location of center of gravity, and the area of the base of the support. So whenever you look at any problem of stability issues, we have to also think of in these lines. Now there are three ways to make a body more stable. So you have to, although you have a problem of stability, you need to address those in the later days. So lowering the center of gravity is one of the conditions for designing for stability. Increasing the area of the base is one more. So you have the I mean, if in case you have the option wherein you can increase the base, therefore you will be also increasing the stability. Now most of the time in engineering, although we say the stability is very important, we most of the time we define instability. So instability is a phenomena which disables an element, member, or a structure to carry further load due to excessive deflection, that is lateral to the direction of loading, and vanishing stiffness. So this would be the right definition, because instability is always important. The structural instability is defined as the condition in which is no tendency for the structure to return to its initial position. So here you see the word vanishing stiffness, and you see that the structure is being subjected to excessive lateral deformations and to the direction of the load, and vanishing stiffness. So this is the definition of stability. Now let's look into, now we have understood something on the basics of the engineering design. The three components are strength, stiffness, and stability. So you have to have the right amount of strength, you need to have the right amount of stiffness, and as well as we need to define, we need to have the structures to be stable. Now let's look into the 2D linear members. Now as you all know, when the length is longer than the other two dimensions, then we call it as a 2D linear member. Since it's linear, then because it has the equation of the first degree, therefore it's called as a linear member. Now these 2D linear member can be a beam, column, or a bracing, or a strut, or examples are many more, and I think you guys deals with the shafts, and these also comes under 2D linear member. Now we are dealing today with the column, so we should know more rightly the definition of a column. A column in general may be defined as a member carrying direct axial load which causes compressive stress of such magnitude that these stresses largely control its design. So basically when you define a member, we call it as any member that is actually loaded as a column. But these actually loaded member are subject to compressive stress. But that stress, the compressive stress, should be predominant. That should be largely controlling its design. It's not just any member that is subjected to compressive stresses are called as a column, but the predominant should be the compressive stresses, whereas other stresses could be as negligible as possible. Then you call it as a compression member or you call it as a column. So when a member carries mainly axial load in vertical is termed as column, while if it is inclined or horizontal, it is also called as strut. So most of the structures can be subjected to the axial loads, but it may not be termed as columns. It could be termed as even beam. Beams can have the loads that are subjected in the axial directions. Now there are various classifications of columns. You can go on. I have listed only few because of the shortage of my slide. I have just placed everything within this slide. So based on the cross section, you can define or classify the column like a rectangle column, square column, and various shapes of columns. Loading: if it is actually loaded and if it is not actually loaded, that means it has got some eccentricity. It can have eccentricity into one direction and two direction. If the loading is eccentric to the center of gravity, then you call it as it is called eccentric loaded column, and it could be in one direction uniaxial bending column or biaxial bending column. Based on the length of the column, you can also predefine. There is a shortest column that is called as a pedestal. You have the short columns. Then you have the intermediate columns and the long column. In general, we define the short column and the long column for today. And later days, I think in the later higher semesters, you'll be learning on the intermediate columns and various derivations of those intermediate columns. There are various materials that is used for the columns, like we in civil engineering we use concrete, steel, and there are various other type of columns. So that could be of various materials, and you can define with respect to materials. In concrete, we use various type of steel. So that is reinforcing steel. We based on that also we try to define the column, like a spiral column or a tight column or a composite column, and so on and so forth. Now, based on the loading, as I said, whether the column is actually loaded or eccentric loaded, we can classify the column as the actually loaded column or concentric column. Loaded with uniaxial eccentricity, you can see that the loading is eccentric to one of the axis. The loading is going to be on one of the axis. Then it is called as uniaxial eccentricity. Then when it is loading with biaxial eccentricity, that means that falls within the quadrant. So if in the loading falls on the quadrant or within the quadrant, then or away from the quadrant, then you call that as biaxial eccentricities. So therefore, you can also classify the column based on the type of column. Now we are dealing with the Euler's column, so therefore we are only dealing with the ideal case where the column is concentric. The loading is concentric. Now, the columns also is can be classified based on the slenderness ratio. I will talk about the slenderness ratio later, but it depends on the length and the various geometrical properties. Now, let's look at the various. As I said, you have the short column. Now, how does it fail? It fails by crushing. Now, it is also called as yielding failure. Now, for the long column, it buckles basically. So, therefore, because of the buckling, it's called as the long columns or long buckling failure. Whereas between these two, there's something called intermediate column, which would try to yield initially and buckle later. So, therefore, we have three type of columns. So, here we have the pedestals, short column, intermediate column, and long column. These are the classification based on the length, slenderness ratio, and behavior. Now, there are various definitions in the textbook. I think it will be discussed in detail by your your subject teachers. There is going to be a definition for short that would differentiate between the long column and the short column. So the long column and short column, you have to talk about the length, the slenderness ratio, and the failure pattern that occurs, and what type of stress it is subjected to. So these would help you, and I just put this on the slide. So as you can see, for the long column, it is subjected to buckling stress only. I will talk about it in the later completely discussion. Will be done in the later slides. The failure occurs purely due to buckling. The slenderness ratio is more than 120. Its length and to the least dimension is more than L by D is equal to. That is, you have this definition. Now, compression member, the failure type. Now we have understood what is the definition of a column, and we are going to be dealing with the columns that are that is going to be subjected to concentric load only, that is the load exactly at the origin or the central axis of the member. Now column we defined as a member which undergoes only compression stresses, as I said, predominantly compressive stress. Now when you are having a column, you should, when it is subject to some type of loading, it fails. So it fails by material failure that happens in short column, and it could also buckle if in case it's a long column. Now, whenever you understand a failure in the experimentations or in any type of studies you do, then you would try to design for that failure. So the column is designed for strength firstly, and then for the stability. So its ability to support the load without experiencing excessive stress. The column stability, its ability to support load without experiencing the sudden change in configuration. Therefore, you would, whenever you are taking any member or any material, you would be subjected to some experimentation. From the experimentation, you will understand what are the failures. You put some assumptions and you will come up with the design steps. So this is what we do, and the columns we design for strength as well as for stability. Now let's look at the shorter column. How does it fail? Now, as you can see from the slide, you can see that the shortest column, that is because it yields and therefore it crushes. You can see one of the examples here. So now because of the load, you can see that it crushes. So the compressive stress is nothing but the applied load divided by the cross-sectional area. Now, there are the failures of a short column resulting from the compression axial forces. Something look like this. If you have a short compression member, if it is a ductile material and as well as brittle material, it is going to be having a different type of failure. When it comes to the ductile, you know it will bulge, and when it comes to the brittle, it will crush and it will fail by shear. So, as you know, the stress is nothing but the applied load divided by the area, or the internal forces divided by the unit area. Therefore, you get, if it is within the ultimate, then therefore it is safe. If it is greater than the ultimate, then it is a failure. Now let's understand the difference between the bending and as well as the buckling. So the bending is the state of stress, whereas the buckling is the state of instability. The load acts perpendicular to the axis of the structural member. Now, but whereas in the buckling, the load acts parallel to the axis of the structural member, and here in our case, it has to be concentric because we are dealing with one of the cases of Euler's column. The failure of bending could be critical. That means it can be critical, and it is quite easily understandable. But the failure of buckling is catastrophic. We'll look into that in the later slides. Buckling, as I said, is a state of instability, and the load acts parallelly to the axis of the structural member, and the structural failure occurs in the lateral direction. The failure of the structure at the earliest stage of loading. So that means the failure occurs at the early stage of loading. Now, if since you are all mechanical engineers, in the later days you will be dealing with the cyclic load and the fatigue load. You can see some failures before it yields. Before the material yields, we could see some failures, but we are talking about buckling, so it is a different type of failure. So in buckling also you see the failure of a structure at the earliest stage of loading. Therefore, it's very very important. Before it yields, it will fail. Therefore, you need to design any structure for component for buckling. Instead of compression failure, buckling arises. This failure is going to be very very catastrophic, and it needs to be looked into, and it's one of the major components of structural design. Now, as I said, how does the long column fail? The long column fails by buckling failure. The strength of the member may be compromised by buckling. Although you may say that you have taken a member that is having a higher stiffness or higher strength, because of the instability issue like the buckling, this may not be the case. The strength loses its stiffness and therefore the structure loses its load carrying capacity to some extent. So therefore it can fail before you anticipate it, or before within before it fails. If in case you have calculated some safe load, it will fail before that. Now, buckling usually occurs when a structure is subjected to compressive load. This is what is being understood by most of us. But buckling can also occur due to tensile load, where this can be seen in most of the mechanical design, mechanical engineering components. In civil engineering, also we have few of the components, but predominantly we have the compression load. But whereas in the mechanical engineering, you have the thermal stresses that are induced in any of the restricted component or restrained components. You see the buckling taking place. Now you can see the compression member failure. Here you have a very small component that is the nail. Okay, and if in case you are applying the force, you slowly by progressively you apply the load to these. Just a minute. Okay. Okay, you've been progressively applying this load, therefore you can see it suddenly fails, and that we call it as buckling. So, as I said, buckling can also occur due to tensile load. That is, the thermal stresses in the railway lane. You can see this is not, this could be a little, modified, but it is exaggerated. But this is what happens. You can see in various components in aerospace industry as well as mechanical engineering. Systems or components, we have various type of buckling that takes place because of the tensile load. And the classification of buckling can be the whole of the system can fail by buckling, or only a portion of it can buckle. So we call it as general buckling or local buckling or overall buckling. So what we are dealing with is the overall buckling. Okay, so in the later days when you are going as you are increasing your knowledge and with the subjects, you'll be learning more of local buckling. Now, general buckling is characterized by the distortion or buckled longitudinal axis of the member, whereas local buckling, the axis of the member is not distorted, whereas one of the components or one of the portion of the components is compromised. Now, you can see in one of the failures of general buckling and as well as local buckling. As I said, I have shown you the building that in later slides I will show you again. You can see the general buckling as well as the local buckling. Now, you also carry lots of finite element analysis on buckling analysis of structures. It could be any structure. It could be cylindrical, or it could be a building type, or it could be any type of simple components. Now you can see some of the failures in the experimentation as well as in the practical side. Some of the tanks, which are water tanks, which are on ground, which is liquid tanks. Also, it could be of any nature, and these are cylindrical in shape, although we say the cylinders are more comfortable taking up the compression. You can see the buckling failure has occurred. This is one of the most important aspect when it comes to the design of elevated tanks on ground. Now, the buckling is very, very important to mechanical engineers when they're designing any type of vehicles and their components. And I think I may not be an expert in this field, but definitely in the later days, I think you guys will have a total insight of design of various components and subject to buckling. So you have various type of elements, and you can see there's a pillar, B pillar, and the C pillar, and you have the unirail. So there are most of the designs when they're concerned with these components, whether it buckles or not, because it has to keep the individual safe. So the unirail, whether it has to be buckling or unbuckling. So kindly note this. You can look into some of the crash tests. You'll understand whether the buckling is allowed on the unirail or not, and the buckling is accepted at the A pillar and the B pillar and the C pillars. So when you're designing any component of any mechanical engineering, you will also deal with the buckling aspect, and therefore this particular subject, the buckling phenomenon or the buckling, is very, very important. So buckling is an instability of equilibrium in the structure. that occurs from compression load or stress. A structure or components may fail due to buckling at loads that are far smaller than that produce material strength failure. So you should understand that the component may fail to buckle or fail by buckle at loads that are far smaller than that material has the capacity. So buckling is catastrophic. So you should understand buckling very very well. So as you can see, when a compression member becomes longer, the role of geometry and stiffness comes into play, and it becomes more and more important. For a long slender column, buckling happens way before the normal stresses reaches the strength of the column. So if in case you have a strength of a column or a strength of a material, some material you know very well, so it will take about some load. But when it is the same material is used into a component which is long and slender, and you're subjected to some type of loading, and if it buckles, you will see that it buckles not to the after crossing the limits of that particular material, but before that itself. So that's very important. So the buckling is very very important to understand. Now you understood that it will buckle. Now the next question is, buckling occurs way before the normal stress reaches the strength of the column material. This is what I made a statement. Now at what load the buckling occurs is the biggest question. So this question was well answered by someone known as the Euler. Actually it is you can see the name here, although it is Euler. Some people define pronounce it as Euler. It is Euler. Most of them pronounce it as Euler. Actually, basically, he was a learned mechanic and he was a Swiss mathematician. Okay, and he derived the formula for the slender column. Actually, basically, he showed that how the critical load would cause buckling in a column, but he used the column to be a straight uni actually loaded, that is loaded to the concentrically loaded, and the conditions of the column is such that it is a straight and it has a pin end. Basically the formula in the Euler equation was named after him for the great contribution to the column theory. So basically you see the Euler buckling load, it's a respect that is paid to Euler for his contribution to the column theory. And you should note that although this is very theoretical, but till today this is the basic for any analysis and design of slender column. If you're walking through the most advanced FEA packages, you'll be looking into these buckling phenomena, and you'll be checking the designs based on the Euler's equations. And the Euler's equation is expressed in this way, and you can see it's pi square EI by L square. So basically here, as I said, Euler was interested in finding the critical buckling load, the load at which the buckling will occur, and therefore it is called the critical buckling load. As I said, the buckling could take place earlier, before the normal stresses have been reached. So therefore this is very important, and the equation is expressed in terms of EI, that is the flexural rigidity, and it is divided by L. So as you can see, very important, if you're a good mathematician, you can see the L is squared. So if the L is squared, therefore that becomes, if you do a sensitive analysis, the length becomes more predominant. Okay, so therefore the length would also be one of the criteria for dictating the terms of buckling. So okay, so therefore the buckling load, which was derived by the Euler, is for the straight pinned ended columns, and this is the buckling load is expressed as the multiple of both end pinned conditions. Now, as I said, the definition of the critical buckling load can be defined as the load beyond which the compression load in a compression member causes it to become unstable and deform. Basically, the structure starts to buckle. The point at which the system converts itself to be unstable and starts deforming, and that point is called, or that loading is called, the critical buckling load, and that point is called the bifurcation point. Now, what are the assumptions that are what are used before Euler brought up this theory? Because as you know, when you're doing some experiments or when you're deriving some equations, to make it simplifier and to reach the solution, feasible solution, and to obtain the mathematical solution as accurate as possible to the reality, so you need to make some assumptions. So assumptions are a supportive tool to make some mathematical simplifications. In this particular theory, the assumptions are the column is initially straight and is uniform lateral dimensions. The second one is the compressor load is axial and passes to the centroid of the column section. The material of the column is perfectly homogeneous and isotropic, and it is pin connected, and therefore the pin joints are frictionless and fixed ends are perfectly rigid. The self-weight of the column is neglected. The column fails by buckling alone. The limits of proportionality is not exceeded. That's very important also. So these are some of the assumptions of Euler's theory. And as I said, this is again the Euler's theory is a function of Young's modulus. It can be any material. Okay, so the material also dictates the critical buckling, and the moment of inertia also dictates the critical buckling. Now, when it comes to moment of inertia, when it is a circular column, as you can see in this slide, I put an hollow and solid. You can see that buckling can take place in any direction. So, because of which you say that there is no one unique solution. Therefore, you have a way of solving such problems. Therefore, you have to know how to derive these equations. So, because it doesn't have a unique solution, therefore it has the multiple solutions, therefore it buckles in various other directions, any directions, and it loses its stiffness. So now if you see in some of the structures or when some of the components, you have the strong axis and the weak axis, so buckling would take place in along the weak axis. So you may have to know what is a strong plane and a weak plane. So along the strong plane and the weak plane, so that you can define the buckling load with respect to those axes. So definitely this also dictates therefore the moment of inertia dictates the buckling load. The next parameter is the length. As I said, it is squared, therefore it is quite sensitive. This parameter is very, very sensitive. So length is plays a predominant role when it comes to the critical load definition. So in short, where we can see that short column fails by compression. So we call it as a short compressive member. For a short compressive member, you calculate the compressive stress, which is nothing but P by A. Now P by A, if the compressive member is made up of some material, it has got some yield or allowable property or the stress, allowable stress. So the force divided by area, it is nothing but the stress. The internal stress should be less than the allowable. Whereas when it comes to the non-compressive member, where it buckles, the buckling load or the load should be less than the buckling load. The critical load, the load that is applied, should be less than the critical load, or it may fail. So therefore, the subject is quite different here when it comes to compressive stress. We are calculating compressive stress when it comes to short column. When it comes to long column, we calculate the buckling load. Now, because of the we define the critical buckling load, the column every column has some limit. That limit that is called the Euler's critical buckling load, the applied load. So if the applied load is less than the critical load, then it is called a stable column. If it is greater than the critical load, the applied load is greater than the critical load, that is called unstable column. If it is equal, it is called neutral column. So here are a few of the slides which will help you to understand the definition, and you can relate why we were discussing on the stable equilibrium, unstable equilibrium, and neutral equilibrium. You can see that this is the analogy, but whereas this is a reality. In reality, you have a column that is subjected to the load, and if the load applied load is less than its critical load, then it is called the stable column. Similarly, we have the unstable column. You can see the type of failure that would occur. If it is greater, it will definitely buckle and it will give away. And when it comes to the neutral, you can see what type of conditions you might be subjected to. Now, the end conditions. Now, as I said, the length is very, very important. But the length, what type of length are we dealing with? Now here the end conditions plays the important role in defining any length. So the let's look into this particular slide. Now, as I said, the factor affecting the strength column includes the slenderness ratio and end condition. The length between the hinges are also known as the buckling length, and this buckling length in the Euler's beam, you took the both side the hinge. Now you can see why he would have taken it, because here you see the buckling length is completely full length. Whereas when it comes to the various other support conditions, whereas fixed, we have a fixed condition, you have pin condition, you have fixed and fixed condition, you can see the buckling length is quite different. Now there is always, a visual misunderstanding of the effective length, that is the point of zero moments, and on the moment diagram, so for the first order analysis. But this, what we are dealing is the buckling shape and the buckling length. For you have the various cases, the effective length is nothing but the distance between these point of inflations or the buckling shape. So we have the buckling length. So the length which I was talking about is more dependent on its end conditions. So you can see here the various end conditions can give you various shapes. Now, if you know what is the support conditions, I think you would have done in engineering mechanics or strength of materials. See, you have the rotation fixed and translation fixed. That means it doesn't allow any translation to take place or any rotation takes place. One of the civil engineering examples or the mechanical engineering examples are here, and here you have one more rotation free and translation free. Although this may look like a fixed condition, you can see there is a small gap here which will allow the rotation free to take place. So this is one of the good examples that will help you to understand. So for different conditions there are different formulas that is derived, although I have not included derivation in my presentation because it's online and things would be done in the classroom. So the buckling load for the pin condition is given by the standard Euler's equation. Similarly, for various other conditions it is derived, and the effective length, that means how the effective stresses where it is being distributed, that length, that is called the effective length. You can see that the length is defined by these. Similarly, you can see at this table the end conditions are defined here, and the general formula that is given by the Eulers is here with a slight modification to the length, that is the effective length, which is here, can bring up the new formula for the Euler's load, that is critical load, and the bent up shape is given by these equations. Now if you see, the Euler's equation is basically dependent on EI, the effective length, and the load. Now the buckling stress. Now we know that the Euler came up with the formula which talks about the buckling load. Okay, now most of the books or textbooks full further give you the buckling stresses. The Euler's formula is used precisely to predict the buckling load if the buckling stress is lesser than the proportional limit of a material. So basically you do the buckling load calculation for this condition, that is the buckling stress is less than the proportional limit of a material. For the purpose of comparison, the Euler formula can be expressed in terms of the buckling stresses. Now how do you do that? All that you have to do is, you have the standard Euler's buckling equation. You know the radius of gyration is nothing but root of I by A, which can be reorganized, and you can see that the moment of inertia is nothing but ER square. So if I just plug it in there, I get a new equation. Here what I've done is, instead of defining the Euler's critical buckling load, I'm defining in terms of the buckling stresses. Okay, so here you can see, if the stresses are less than the critical buckling stresses, it is safe. If it is greater or equal, it is going to buckle. So generally the equations are the purpose of for the purpose of comparison, the Euler's formulas are expressed in terms of buckling stress. Now, as I said, what does it depend on? Again, it depends on E, L. As you know, this is again got from the standard Euler's equation. But here, the dimension of the cross section, that means the radius of gyration, comes into play. Now, as you saw that we tried to plug in the equation and we got a new equation, and here by reorganizing you get something called the lambda here, that is nothing but L by R, that is this is nothing but the radius of gyration. So this is defined slenderness ratio, that is the slenderness ratio is a function of effective length and radius of gyration. Radius of gyration is nothing but root of I by A. All that I did is I plugged in the radius of gyration, the area in place of I, and after that by replacing L by R, that L effective length by radius of gyration, I get a lambda, which is nothing but a new parameter, that is nothing but the slenderness ratio. Now this slenderness ratio is very very important, and this slenderness ratio defines the type of system, that is whether it is a short column or the long column. The length is LE is nothing but the effective length, the column length, and it depends on the support condition. This is the effective length is dependent on these two. The radius of gyration is dependent on I by A. If you look closer, now these parameters can really define your whole system behavior. The length is going to dictate your behavior, the support condition is going to dictate your behavior, and if you see closely here, the I and A, the effectiveness of using the material is very clearly depicted in the radius of gyration. Therefore this is a complete formula to understand the critical buckling. So most of the time what they do is they try to find the critical slenderness ratio. Now that is, to know whether the column is short or long, we find the critical slenderness ratio using Euler's formula, and when you just supply that formula with the yield strength, the modulus of elasticity, and you will get the critical slenderness ratio. If the critical slenderness ratio is greater than the slenderness ratio of the column, it is called a short column, and if the critical slenderness ratio is less than the slenderness ratio of a column, it is called as long column. Now let's look into the effective length coefficient and theoretical value of K. As I said, there are various end conditions and various end conditions of various effective lengths, and as I said, it is nothing but the influence area where the stresses are predominant and effective there, and that dictates the effective length. Now in the textbooks or in most of the handbooks, you find there is something called the theoretical K values. The theoretical K values for various end conditions for the column buckling is given here. As you can see, higher the value, more likely to buckle. So the higher the value, the more likely to buckle, because the effective length is going to be higher. So therefore you should know that in order to get the effective length, all that you do is, if you have the length, if you know the length of the column and you know the end condition, by multiplying this theoretical value K into length will give you the effective length. Now, as you can see in the books, again, they would have given you something called recommended design value. In various engineering fields, even in we deal with concrete and we deal with steel, they also recommend various design values. Now, why is the design value different from the theoretical value? Because to take into various uncertainty in practice. So that's why you have this design value. So when you're doing a design value, now there is also, when you're doing the theoretical analysis using FEA packages, you take the theoretical value for few of the materials like steel, where the assumptions holds very good. All the assumptions like the homogeneous, isotropic, and everything holds good. You can look into these values and plug in and get the values. But if in case you suspect that material is of a lot of uncertainty, then you may have to go with the recommended value. But when you're dealing with wood, which is quite quite a complex system, so therefore you will be always going with the recommended K values. Okay, so I think I'll be ending up in just 2 more minutes. I hope that is fine.
Yes, sir. Yes, sir. Yes, sir.
Fine. So the end conditions, though, as you can see, you have the length, you have the end conditions of a column here, and because the column is fixed, you have the K value to be 0.5. You know the column size is reduced. Now similarly, if I take various conditions, here you have the 10 meters column, and the end condition, you can see the column length is changed. So that the end conditions dictates the effective length. And as I said, now let's look into how the end conditions and the effective length dictates the buckling load. Now let's take a condition, and this should be helping you out to understand this particular subject very well. Now if you have an end condition of a column that is being fixed on both ends, you have that column length is 10 meters. Because of this end condition, it almost reduces by half. That means the length is reduced by half, but load carrying capacity, if you plug in this equation into the equation, the load carrying capacity of this particular column is increased by four times, the four times. So therefore this is very very important. Since the both the ends are fixed, although the length is reduced by half, the load carrying capacity increased by four times. Now if you change the end condition here, as you can see, in case of the flat post or something like this, you have the k value to be 2. Therefore the length of the member is increased twice. So you can see, because of that, the length is increased twice, but the load carrying capacity is 1/4. It is reduced 1/4. So this plays a very important role. By understanding these type of basic understanding, you can easily tune your system or design your system such that you get the maximum benefit from the engineering designs. This is all about the Euler's equations, how you can use it practically. The limitations are the above formula or the Euler's equation is applied only for the long columns. If it is a short column, you may have to you may not be able to use it, or if it is an intermediate column also, you may have to use various other theories. As the slenderness ratio decreases, the crippling stress increases. Consequently, if the slenderness ratio reaches to 0, then the crippling stress reaches infinity practically, which is not possible. If the slenderness ratio is less than certain limits, the crippling stress is greater than crushing, which is not possible practically. Therefore, up to a limiting, Euler's formula is applicable within the critical. So therefore, you should understand that if you just put an equation, that means if you graph the Euler's equation, show that the predicted buckling stress is quite large for a small value of slenderness ratio. As you can see here, for the small value of slenderness ratio, you can see the buckling stress are quite large. You can see here, but at these levels the critical buckling exceeds the capacity of the material, and that means if you have a material of Fy, that is, if it has had a yield strength of Fy, it is already crossing that, therefore it cannot be applied. So therefore you should understand that this particularly you should take whether it the when you are taking it the buckling load, you may have to take the minimum of the Fy or this particular stress, that is theoretical maximum compressive stress. So therefore there are a lot of limitations. I believe I will just skip through this, because it is now since you know that the Euler's buckling load is applicable for the long column, and it is for the having the lower slenderness ratio, it may not be applicable. You may have to look into various things, and this can be discussed or looked into the textbooks. I'll show you some of the examples in civil engineering. In civil engineering we have various columns and various types of columns which we use, and these are concrete types, concrete or steel or precast. And you can see we also classify these columns based on the loading, as usual, that you do in mechanical engineering also. And you can see the similar type of failures that occurs in civil engineering also: buckling failure, compression failure, and shear failure. And these are some of the practical examples. Now you can see this is the failure due to buckling, and here you can see crushing. We also do the concrete crushing test. So here this is also a pedestal, and this is the short column, so that also fails by crushing. You can see that these two is depicted in this picture, and these are controlled by using tie rods, and that is these you can see some of the pictures that shows the buckling of the column and the failures due to. And when we design, we give more importance. When we design, we give more importance to the hand calculations. The hand calculations plays a major role. If you see, one of the famous designer, aerospace designer, said that what can be designed on a back of a waste envelope cannot be designed using a computer. So he said that if you whatever you scratched on your paper, that is more important, that dictates your design more than what you do on a computer, because it gives you a thorough understanding. So these are few of the design failures of column. As I said, this is one of the practical site where I was involved, and this is the structure. You can see, because of the buckling, this whole structure is in good, although it was in a good shape, because of the buckling, the whole structure is questionable. It's totally unsafe for functioning. So These are the few of the practical examples, and you can see here the local buckling, which I said. The global buckling is for the whole structure, the local buckling, and it also, if you know the proper theory, you can also provide some retrofitting schemes. Now I have so I thank you one and all for your patient hearing. I hope I've just taken the right amount of time. Because of the start, I think I was able to take extra minutes. Thank you one and all.
Thank you, sir. Thank you, sir. Sir, we have questions from our students.
Yes, please. Hello.
Yes, there is 1 minute.
Yes, please.
Sir, will the buckling load be added to all the meteorologies?
Sorry, can you please repeat?
Will the buckling load applied all to all the materials
Okay.
available?
Yeah. See this. Okay. Now any component is made up of any material. Okay. You have a component that is made up of some material. If that component is subjected to some loading, and the component has to be the long component, or the slenderness ratio will define whether it is a long column or a short column, since it's subjected to compressive stress. If it is subjected to compressive stress and it is long column, you can definitely apply the Euler's theory and the buckling load concept.
Okay, sir. Thank you, sir, Professor Mantesh. So thank you very much for your valuable time and sharing your knowledge with our students. On behalf of Department of Mechanical Engineering, I thank you, sir.
Thanks, Professor Mantesh Koti, for inviting me. It's my first lectures at PS University as the outside the consultant. Thank you for inviting me, and thank you for the patience hearing for all the students. I wish them all the best for their internals.